So, what if I told you that our most common building material, concrete, didn't actually have to break? What if it could bend? Well, today we're diving into a material that does exactly that. It's called engineered cementitious composites, or ECC. And to really get why it's such a game changer, we first have to talk about a pretty fundamental problem with the concrete we use absolutely everywhere. And yeah, that problem lies with the material we use more than anything else on this planet, except for water: concrete. For all its incredible strength, conventional concrete has this one huge Achilles heel. It is incredibly brittle. And that brittleness, it's at the very heart of some of our biggest, most expensive, and frankly, most dangerous infrastructure problems. Okay, let's get into it. You see, concrete is fantastic under compression, when you squeeze it. But the moment you pull on it, the moment you put it under tension, it fails. It cracks. And we're not talking about tiny little cosmetic cracks. We're talking about large, uncontrolled fractures that can lead straight to catastrophic failure. The fallout from this is literally all around us. Think about an earthquake. That brittle failure can be absolutely disastrous. Or just look at a bridge deck or a building facade. Even those smaller cracks become super highways for water and de-icing salts to get in. And what does that do? It corrodes the steel rebar inside, causing the concrete to literally pop off. It creates this endless, incredibly expensive cycle of repairs. It's a massive drain on our resources and a very real public safety concern. Okay, but what if concrete didn't have to shatter? What if, instead of just breaking, it could actually bend? Well, this is where our protagonist, engineered cementitious composites, finally enters the story. You see, ECC was designed from the micro level, from the ground up, to overcome this exact flaw. Now, this is not just concrete with some fibers thrown in for good measure. No, ECC is a meticulously designed composite. It's all about the very specific interaction between the cement matrix and these specialized microfibers. This allows it to do something called strain hardening. So when you pull on it, it doesn't just snap. Instead, it forms this whole network of incredibly fine microcracks, absorbing energy and deforming, almost like a piece of metal would. And this right here, this just perfectly illustrates the difference. Just look at the tensile strain capacity. That's how much it can stretch before it fails. EC can deform 300 to 500 times more than conventional concrete. That's not a typo. So while regular concrete gives you this sudden, catastrophic failure, EC gives you a graceful, visible deformation. It basically gives you a warning, and for structural design, that changes absolutely everything. So this isn't just some lab curiosity, right? Let's take a look at how ECC is already out there solving real-world infrastructure challenges. We're going to walk through 3 case studies that really show off just how versatile this stuff is. First stop, Japan, a country where seismic resilience is obviously a massive priority. Now, in skyscrapers, you have these things called coupling beams. They connect core walls, and they're designed to absorb the energy of an earthquake. The problem is, with traditional reinforced concrete, these beams need incredibly complex steel cages inside, and they often get severely damaged after a quake, which means very expensive repairs. This was the exact challenge they faced in buildings like the 60-story Kitahama Tower in Osaka. Okay, now what's really fascinating here is the data from tests that simulate an earthquake. The conventional beam shows what's called pinching behavior. You can just see how it loses its stiffness and strength with every shake. But the ECC beam, it just maintains its ability to carry the load and absorbs vastly more energy. For those of you studying seismic design, this is a total game changer. It essentially acts as a structural fuse that's not only stronger, but it's damage tolerant, which dramatically slashes the need for repairs after an earthquake. All right, next, let's head over to Michigan in the US. Anyone who's ever driven over a bridge knows that constant thump-thump of the expansion joints. Well, those joints are a massive headache for transportation departments. They're basically a weak link. They let water and salt leak through, corroding the steel below, and they're a constant source of maintenance. The big challenge was, could we just get rid of them? So, to test ECC's durability, they did a side-by-side patch repair on a bridge. And the results? They're just astounding. After 2.5 years of heavy traffic and brutal Michigan winters, the normal concrete patch had a crack nearly 4 millimeters wide. It had to be repaired all over again. The ECC patch, it only showed stable microcracks, less than 50 microns wide. We're talking thinner than a human hair. It's this incredible durability that allowed engineers to create a link slab and just replace that problematic expansion joint completely. For our final case, we're heading back to Japan, to the Mitaka Dam. Here, the challenge wasn't earthquakes or traffic, it was water. The 60-year-old concrete face of the dam was all cracked and deteriorating, and it was starting to leak, which, as you can imagine, is a pretty serious threat to its structural integrity. So instead of a massive, super expensive overhaul, the solution was remarkably elegant. They used a sprayable version of ECC and applied it in a thin 30mm layer right over the damaged surface. Because ECC's microcracks are so unbelievably tight, the material itself is highly impermeable, even when it's being stretched. This thin layer effectively created a durable, watertight shield, extending the dam's service life in a major way. So we've seen these really specific examples, right? But let's kind of zoom out and synthesize what this all means. Why does this material matter so much for the future of our infrastructure? It's all about connecting these unique material properties to real-world value. This table really connects the dots. For seismic safety, it's all about that high energy absorption. For bridge decks, it's that killer combo of ductility and sheer durability. For keeping water out of dams and tunnels, it's the intrinsically tight crack width that makes it so watertight. And for repairs, its damage tolerance stops that dreaded reflective cracking, where old problems just reappear. You see? Each application leverages a specific, engineered property to solve a multi-billion-dollar problem. So ECC is clearly this amazing, high-performance material with proven benefits, which leads to the obvious question: what's stopping it from just replacing conventional concrete everywhere? Well, the challenges are pretty clear. First up, the initial material cost is higher. Now, life cycle cost analyses often show it's way cheaper in the long run, but that upfront cost can be a barrier. Second, there's just a lack of familiarity. Engineers have spent a century being trained to think about concrete's strength and compression, not its ductility and tension. And finally, the design codes themselves are still playing catch-up, which makes it harder to really take full advantage of everything this material can do. But, for a room of innovators and future engineers, these aren't dead ends, they're research challenges. How do we optimize ECC to bring down the cost? How do we develop brand new design methods that fully leverage ductility? How can we help create the next generation of building codes? This is really where the next wave of innovation is going to come from. And as Victor Lee, the material's main developer, puts it, it's the real-world applications that truly drive the material forward. Every new project gives feedback that helps refine the material and inspires brand new uses. So the practice informs the science, and the science then enables new practice. It's this perfect, virtuous cycle. And that really is the ultimate takeaway here. ECC is so much more than just a better concrete. It is proof that the fundamental limitations of our most common materials are not set in stone. It shows us that through deliberate, science-based design, we can actually engineer properties we once thought were impossible. So the real question is, what will you design next?